This is a revision podcast for Edexcel IGCSE Physics, and this is on Topic 1, Forces and Motion. When you see a distance time graph, try and identify from the axes what the graph is telling you. This line starts at the origin at 0 meters and after 20 seconds has reached 10 meters away, and it does so at a steady rate. It therefore represents a constant speed or velocity. This line stays a fixed 10 meters away from the origin, so it represents a stationary object. This line is moving away at a constant speed, but the rate of change of distance with time is greater, so it represents a faster speed. A downward sloping line represents a negative velocity, travelling back towards the origin. The gradient of the line is the velocity. Velocity means speed in a given direction. Velocity is a vector. For example, you could say something was travelling with a speed of 20 meters per second, but to specify the velocity, you need to specify the direction as well. You need to know the speed formula, which is speed equals distance over time, and the standard units for speed would be meters per second. Displacement means distance travelled in a given direction, so displacement is also a vector. Velocity is the gradient of a displacement time graph. Let's look back at the graph that we've just looked at. Can you calculate the speed during the first 20 seconds of the graph? You'll remember that speed is the gradient. That's the distance travelled divided by the time taken. So 10 over 20 would be half a metre per second. Can you calculate how far the object is from the start after 60 seconds? Well, this isn't a difficult calculation. You look across to 60 seconds and you read from the graph that it's 40 metres away. Can you calculate the speed during the last 40 seconds? It went from 40 metres back to the origin at 0 metres. So the speed is 40 divided by 40, or 1 metre per second. The velocity would be -1 because it's travelling back towards the origin. When was the object travelling the fastest? Without a calculation, you can see it's the steepest part of the graph, so between 40 and 60 seconds. You could calculate the speed here, it's 1.5 meters per second. Velocity time graphs may look very similar to displacement or distance time graphs, but the features are completely different. Again, try and use the axes to tell the story of the graph. So this line represents something that at the beginning is travelling at rest. It isn't moving. But after 10 seconds, it's moving with a velocity of 40 meters per second. In other words, this represents acceleration. A horizontal line keeps the same velocity of 40 meters per second, i.e. it doesn't change its velocity, but is still moving. So it represents a constant speed. This line is also increasing its speed from 40 to 60 over 10 seconds. It represents acceleration, but the acceleration is not as much as it was in the first phase of the graph. This downward line represents deceleration. It slows from 60 back to rest, so it's a braking or deceleration. The gradient of the line represents the acceleration, and we can also show that the area under the line represents the distance travelled. So the definition of acceleration would be the rate of change of velocity. That means the change in velocity divided by the time taken, or acceleration is final speed minus starting speed over time for the change. You've got to be able to remember this formula and note the units. Meters per second are the standard units of velocity, seconds for time. That means acceleration comes out to be meters per second squared. Let's look back at the graph and see if we can calculate some values. How fast was the object going after 10 seconds? Use the graph to tell the story. After 10 seconds, read off the velocity from the graph. it's 40 meters per second. What was the acceleration from 20 to 30 seconds? We need to look at the change in speed between 40 and 60. So that's a change of 20 meters per second in 10 seconds. 20 over 10 is 2 meters per second squared. What was the deceleration between 30 and 50 seconds? At 30 seconds, it was travelling at 60. At 50 seconds, 0. So the change in speed is 60 over 20 for the acceleration makes minus 3 meters per second squared. Minus because it's decelerating. How far did the object travel altogether? You'll remember that distance travelled is area under the graph. So we need to calculate the area of each of these segments. Starting with a triangle, the area of a triangle is a half base times height. That gives 200 meters. Then there's a rectangle, and then there's a rectangle and a triangle, or a trapezium, and then another triangle. So the total distance travelled, you add up the area of all the segments, and that gives 1700 meters. A force is a push or a pull of one body on another. I've listed here a number of different types of forces you should know about. I suggest you pause this slide and make sure you understand what all of these forces are. Forces are vectors. Vectors have size as well as direction. Vectors are well represented by arrows. The length of the arrow represents the size of the force, and the direction, of course, by the direction in which the arrow points. A resultant force can be calculated by adding all of the forces acting in one direction. For example, on this car, 120 newtons pulls forward and 20 backwards, so the resultant force would be 100 newtons forwards. If there is no resultant force, or the resultant force on an object is 0, then it doesn't accelerate. Now that can mean it's either at rest or it continues moving at a constant velocity. In the case of a car driving along at a constant speed, there will be a forwards force provided by the wheels and the engine, and there will be a backwards force provided by friction and air resistance. This car could be travelling at a constant speed. The formula that relates force, mass and acceleration is F equals ma, and you need to know this formula. The standard units for force are newtons, and a newton is 1 kilogram that's been given an acceleration of 1 meter per second squared. This car is going to accelerate towards the right. To calculate the size of the acceleration, you first need to work out the unbalanced force, F, and then rearrange this equation to make A the subject. So A would be force divided by mass, which is 100 newtons, the unbalanced force, divided by the mass of the vehicle, which is 0.2 meters per second squared. An object that accelerates changes its velocity. As velocity is speed in a given direction, this means it must be either changing speed or changing direction. An object travelling in a circle is therefore accelerating, as it changes direction all the time. The acceleration is towards the centre of the circle. The velocity at any one point is at a tangent to the circle, and the acceleration is always along the radius of the circle. Weight is the effect of gravity or the gravitational field, and weight is a force measured in newtons. On Earth, the gravitational field strength is 10 newtons per kilogram, and this is given on the front of the exam paper, but you do need to be able to use the formula. It says weight is mass in kilograms times by the gravitational field strength. This is sometimes written as in units meters per second squared. Let's do an example calculation involving weight. This skydiver has a mass of 80 kilograms, so his weight is 80 times by 10, or 800 newtons. If we apply the acceleration formula we saw a few slides ago, you'll know the acceleration will be force divided by mass. 800 newtons is his weight, divided by his mass, gives an acceleration of 10 meters per second squared. This gives a clue why the acceleration due to freefall is also equivalent to the gravitational field strength. Let's consider the stages of free fall. Initially, only your weight acts when you jump out of a plane. And your weight force, as we've just seen, causes you to accelerate at the rate of free fall. After a little while, your speed increases, and that means that the drag force on you also increases. So an upward force starts to reduce the unbalanced force. This means that your rate of acceleration will be smaller. After longer still, the drag force will eventually have increased until it's the same size as the weight. At this point, there's no resultant force, and so the acceleration is zero. And as the skydiver can't get any faster, the drag force can't increase. And this is your terminal velocity, the fastest speed you'll reach in freefall. After a while, you'd open a parachute. The increased surface area will increase the drag force. A larger drag force results in an upwards net force, and this makes the parachutist decelerate or slow down. As the speed reduces, the drag force decreases. When the drag force is reduced until it's the same size as the weight, then the skydiver can no longer accelerate. So he's reached a slower terminal velocity. Can you try and imagine what a velocity time graph would look like for the whole fall? Let's have a look at that velocity time graph. At the beginning, the velocity must be zero, and it will increase initially. The initial gradient should be the acceleration due to free fall, or 10 meters per second squared. But eventually they reach a terminal velocity. So the line will flatten out to the point of terminal velocity. At this point, the parachute is opened and the velocity decreases. They decelerate rapidly at first, where there's a large drag force, and less until the two forces are equal. And at this point, they've reached their lower terminal velocity. Eventually, of course, they'll hit the ground. Let's look at another application of a velocity time graph. When you see a hazard and you're driving at a constant speed, it'll take a little bit of time before you react. The moment you see a hazard, you will take time before you can press the brakes. From that point on, you'll apply a constant force at the brakes, and the car will slow down at a constant deceleration. This would be called the braking time. Once the brakes are pressed, the car should slow down at a uniform rate, according to the formula we've just looked at. The area under a velocity time graph, remember, is distance. So the thinking distance is the area of this rectangle, and the braking distance, the area of the triangle. The total stopping distance would be the thinking distance plus the braking distance. Various factors will affect the ability of a car to stop. Here are a few. The thinking distance would be affected by the conditions of the driver, whether or not they were under the influence of drugs or alcohol. You might argue that visibility will also affect your ability to react. The braking distance is going to be affected by factors relating to the car. So the road condition, the tyres, the brakes, the speed of the car, and the mass of the car, because these also affect the ability of the car to decelerate. Momentum is the quantity you get if you multiply the mass of any object by its velocity. So it has units of kilogram meters per second. And the rule that you have to understand with momentum is that momentum is always conserved. Let's look at an example of conservation of momentum. Imagine a truck moving at 10 meters per second. Let's calculate its momentum. So you do mass multiplied by velocity, which would be 20,000 kilogram meters per second. Now imagine that truck collides with a stationary car, which is 500 kilograms in mass, and the two vehicles combine and move off together. Calculate their combined speed. Momentum in this collision will be conserved. So while the truck initially had 20,000 kilogram meters per second of momentum, the car and the truck combined will have a total momentum of 20,000. The new mass of the vehicles together is 2,500 kilograms because they've become stuck together. So the new velocity will be momentum divided by mass. Use a triangle to help you rearrange if you need it, which would be 20,000 over 2,500 or 8 meters per second. Separate scientists need to be able to use the equation change in momentum over time taken is the force applied. This is printed on the exam paper. It's another way of expressing Newton's second law, F equals m times a. Let's put it in practice. During the collision between the truck and the car, the truck slowed down by 2 meters per second. This allows us to calculate its change in momentum. It had a mass of 2,000 and it's changed its velocity by 2, so the change in momentum of the truck is 4,000 kilogram meters per second. If you're told it took 0.4 seconds for the collision to take place, that's the time in which the car is being struck by the truck, you can calculate the force exerted by the car on the truck, or equally by the truck on the car. You'd use the equation change in momentum over time, so that was 4,000 divided by 0.4, which is 10,000 newtons. This large force is also exerted on the driver, and as a result they might suffer injury. That's why it's probably best to try and avoid traffic collisions. There are a number of factors that affect the safety of a vehicle, and you could explain these in terms of change in momentum or just in terms of Newton's laws, F equals ma. Crumple zones, as shown here, increase the time to stop, and that decreases the force applied to the driver. Airbags also increase the time to stop, and this decreases the force acting on the driver. They may also reduce pressure. And seatbelts attach the driver to the seat so that the driver slows at the same rate as the car. This means that the driver no longer decelerates rapidly when he hits a sharp object. Newton expressed his third law like this: for every action there is an equal and opposite reaction. In Newton's day the word action meant force, so you'd probably express this a little better in today's terminology. I would say when object A exerts a force on object B always exerts an equal and opposite force on object A. And I'd go further and say that this is always the same kind of force. If you think back to the collision between the car and the truck, we calculated that the car would push the truck with a force of 10,000 newtons. That's going to be the same as the size of the force that the truck puts onto the car. These are equal and opposite Newton's third law pairs. A moment is the turning effect of a force. A moment is equal to the force itself multiplied by the perpendicular distance from the pivot. Perpendicular means at right angles. So this force is 1 meter away at right angles from the pivot. And objects are in equilibrium when the sum of forces acting on them are 0, and also the sum of moments. If there's a greater moment pulling in one direction than the other, the object will rotate. So let's decide if this beam is in equilibrium. You'd have to look at the moments. To cause this to turn anti-clockwise, on the left-hand side of the pivot, is a force of 10 newtons, 2 meters away from the pivot. So that gives an anti-clockwise moment of 20 newton meters. On the right-hand side, you also have 20 newton meters, and so this beam is in equilibrium as the moments are equal. As a vehicle crosses a bridge, the pivots have to supply different forces depending on the position of the load. Pivot A has to supply an upwards force that will decrease as the vehicle moves across to the right. And pivot B has to supply an upwards force that's greatest when the vehicle's over on the right and 0 when the vehicle's all the way over here. In order to work out the size of the force, you'd need to take moments about pivot B. And to work out the size of force B, you'd need to take moments about pivot A. That's assuming that you knew the size of the load. The centre of gravity of an object is the point through which all of the weight of that object can be thought of to act. and a force arrow showing its weight should be drawn downwards from that point. It's at the centre of a uniform shape, but it may not be at the centre of all objects, and it can even be outside the object. This diver, centre of mass, is outside of his shape because he's bending over. To find the centre of mass or centre of gravity of a uniform shape or laminar, you'd suspend it from one point, and you'd hang a weight on a piece of string to show you which direction is vertically down. This line shows you that the centre of mass will be vertically below the pivot point, so it must be somewhere along this line. If you repeat at a second location, as you can see on here, the point where these lines cross will be the centre of mass of that laminar. Many devices use moments as force amplification devices. When pulling a nail out of some wood, the pivot point is very close to the wood. A large distance is in place between the pivot and where you pull from, and a short distance in place from where the force acts. If you equate the moments, the red moments balance the blue moments on the diagram. So large F multiplied by D is small f multiplied by D. You can see that the large force applied outwards is a ratio of little d over big D. So the ratio of distances here, small d divided by big D, gives you the amount of times that the output force is bigger than the input force. The centre of mass determines whether an object will be stable or not. Will this bus stay on the slope or will it tip up? Well, the blue dot represents the centre of mass. This may be slightly nearer the bottom of the bus than the top because of the mass of the engine will be near the bottom. This bus is stable. It's stable because the centre of mass is to the left of the pivot point, and so that causes a moment on the bus, causing it to rotate anti-clockwise, and therefore turning it back up the slope. This bus looks unstable, but to prove it's unstable, you look at where the centre of mass is. The centre of mass is to the right of the pivot point, and therefore the moment would be caused to rotate the bus clockwise, around or down the slope. Extension is how much longer an object has become compared to its original length. So if this is the original length of a spring, the extension would be this measurement here. You'd calculate extension by taking the new length and taking away the original length. Extension is directly proportional to applied force for springs, and those materials are said to obey a Hooke's law. If a material is stretched beyond its elastic limit, it no longer obeys Hooke's law. Let's look at the force extension graph for a spring. It will be directly proportional. The greater the force, the greater the extension, and these will be linked directly proportionally, so you get a straight line graph that passes through the origin. Eventually, the spring has passed its elastic limit, and at that point it's starting to stretch permanently. It will no longer return to its original length, and it no longer obeys Hooke's law. A metal wire behaves similarly to a spring. It obeys Hooke's law for a short region, and that's because the bonds between metal atoms behave similarly to springs. If you keep pulling on a metal wire, eventually it will be past its elastic limit too, and it will stretch permanently. And that happens when the metal atoms no longer are attached to their neighbours with these spring-like bonds, and they're able to slip past each other. Elastic bands do not obey Hooke's law. The structure of an elastic band is a polymer chain, and when you pull it, it's quite stiff initially, but eventually it becomes easier to stretch as the polymer chains unravel. At this point, the polymer chains are now themselves being stretched, and so it becomes harder to stretch. Orbits are caused by the force of gravity. Gravity pulls any two objects with mass together. The bigger the mass, the bigger the force. Moons orbit the Earth or other planets, and the Earth and other planets orbit the Sun. On Earth, the gravitational field strength is 10 newtons per kilogram, but on the surface of different planets or moons, it's going to be different. The size of the gravitational field strength depends on the mass of that planet. Gravity also causes comets to orbit the Sun, and they have a very large elliptical orbit. As the comet is further away from the Sun, the force of gravity is very small, and it travels and accelerates slowly. The force of gravity accelerates it towards the Sun, so it will be travelling at its fastest point here. That's also the point at which it's accelerating the most. You can calculate the orbital speed using this formula. Orbital speed is 2 pi times by the radius over the time period. This, of course, assumes that the orbit is a circle. This formula is provided on the Edexcel IGCSE paper. Let's use that formula. What's the speed of orbit of a satellite orbiting the Earth at a height of 200 kilometers above the Earth's surface that takes 88 minutes to orbit the Earth? And the other bit of data you need is the radius of the Earth is 6,400 kilometers. Firstly, I'd use some standard units to make sure the answer comes out in meters per second as required by the question. So don't forget that the total radius of the orbit is going to be the radius of the Earth plus the height of the satellite. So that's 6.6 million meters. The time period is 88 minutes, and that transfers into 5280 seconds. And now we can calculate the speed using the formula 2 pi r over t, which comes out to be 7,800 meters per second, about 7.8 kilometers per second. The Milky Way is our galaxy. It contains hundreds of billions of stars. The solar system, you are here, somewhere in an outer arm. And the universe consists of many billions of galaxies. This is one of my favourite photographs taken by the Hubble Space Telescope. Every one of these dots is a distant galaxy, each containing hundreds of billions of stars.